And a stepper controller be created using an ESP32 in just a dozen lines of code. To start with, I'm going to use a PCF8574 so that the ESP32 can use I2C to control two steppers at once using only 2 pins. Since a driver is required anyway, this seems a nice simple option. And for switching the current, I'll use a ULN2803 8-channel Darlington transistor array. This design fits nicely onto a small perf board. This is basically the same circuit that I used in my flip card clock. Connection is pretty easy. VCC and ground connect to the 3.3 volt power supply. The bottom left 3 pins set the address and all 3 are simply grounded. If you want to put a number of PCF8574 chips on the same I2C bus, the bottom left pins are used as 3-bit address values. The base address is 20 hexadecimal with all 3 pins tied low. The I/O pins on the PCF8574 are fed 100 microamps when set high and are pulled to ground when set low. 100 microamps is not enough to drive the input of a ULN2803 reliably. So each of the 8 I/O pins needs to connect to the ULN2803 with a 10k pull-up resistor. A 10k by 8 Resnet, similar to this picture, will work really well. These are cheap and I stock about 50 of each of the types that I use frequently. Be careful when purchasing, as there are lots of different pinouts available. The type that I stock have one common pin that connects to each of the other 8 pins through the 10k resistors. When I use these, I do a quick check with the multimeter before fitting, just to make sure that I have the right value and orientation. This is the basic circuit for the Resnet. Finally, we have the ULN2803. This is a transistor array with logic level inputs. This means they can be connected to 5 volts with no current limiting resistor. Though you may recall that the inputs are pulled high through 10k pull-up resistors. PCF8574 is being powered off 3.3 volts, so we are actually feeding it with a 3.3 volt signal. ULN2803 handles this fine though. This is the basic circuit for a ULN2803 channel, and as you can see there's no path for any voltage to flow back to the input. In fact, the chip can switch up to 50 volts. Consult the data sheet if you intend to work with significant voltages or currents though. The ULN2803 works like most transistor driver circuits by connecting the output load to ground. This means that all of the currents switched through the device will all sync through one pin. Whilst the ULN2803 has impressive ratings, you must factor into your planning how many channels are expected to be active at any time, as well as the duty cycle. Duty cycle is simply the ratio between on and off that's expected. For 2 steppers, it's pretty simple. At any one time, 2 channels will be permanently on. These are just then sequenced to rotate the motors. The chip can easily handle this load. The last pin to explain is the VCC pin. This actually doesn't power the chip at all. It's marked here as VCC because that's what it is connected to, but it's not actually used as a supply rail for the chip. Inductive loads such as motors, steppers and solenoids produce a back EMF that needs to be clamped back to the supply rail to prevent interference. The pin connected to VCC is the clamp output, which must always be connected to the same supply rail as the loads. The ULN2803 will work without the pin connected, but this should not normally be done. I believe that it may be safe to do so for non-inductive loads such as LEDs, but it's a good habit to connect it regardless. Now, stepper. For this I used a 5 volt geared stepper. These are often referred to as valve steppers. I think that's because they are made for air conditioning systems. These are cheap and are available in 5V and 12V versions. Note the part number on the back of the unit. Look this up in eBay and you will find plenty of sources. Here is the pinout. The phase order is basically orange, yellow, pink, blue. Well, one thing's for certain, this one will be a fail. But I knew that going into this project. There are plenty of dedicated stepper controllers out there that just need a direction and step input. If you're using one of these modules though, there's no need for a tutorial, as it's just a simple matter of writing to a couple of pins. I've gone down the path of using the PCF8574 and ULN2803 chips because they are both cheap in small quantities. They are also both very useful multi-purpose chips that are great to have around. And besides, we are controlling two steppers with only 2 pins. And those 2 pins can still be used for other I2C devices. We could even control another 14 steppers this way. The logic is pretty simple. For each stepper, we use a single byte with 10001000. Then we rotate it left or right to sequence the stepper. Although we only need 4 bits, it's easier to rotate an entire byte. The 2 bytes are then masked into a 3rd byte using the first nibble of one and the second nibble of the other. The result is then sent to the PCF8574 to control the steppers. Here is a simulation. And here's how it works. First, we need to include the wire library for all the I2C functions to work. Next, we declare the 3 bytes used for the stepper sequencing. Ignore the global declaration for N here. It was only done to cut the number of lines by eliminating a declaration. The send stepper function is only there to take the output byte and send it to the PCF8574. Note the 0x20, which is the address of the chip. The step function is given a motor number, which is either 0 or 1, and a Boolean value to represent the direction. These 2 lines rotate the byte for the specified stepper forwards or backwards based on the direction flag. We AND the 2 bytes with a mask. Then we OR the results together to provide the 3rd byte, which will be sent to the PCF8574 in the very next line. This is the function that sets the default values for the arrays, then powers the appropriate windings in the steppers. I could get rid of N completely and initialize the values at the top as part of the declaration of the stepper array. This would also mean that I don't really need init stepper, but for now I'll leave it as is. So now, we just use setup to call the init stepper function. In the loop, I'm just making the steppers move around independently. So now, let's test it. Now, those changes. It's kind of squashed, which is probably cheating, but it's 12 lines. Pass. Please feel free to share any experiences with this code and let us know what your experiences with these steppers has been like. I'm always keen to hear about other people's projects.